Hey guys, I'm making this energy review, this Unit 3 review. Students really like my Unit 2 dynamics one, so that's kind of my motivation for making this one. I'm going to go over Unit 3, and I like Unit 3 because, one, it's the shortest unit we've done so far. Most of the units after this are a lot shorter than the first two units. And I think you can redo a lot of the problems you've done in the past. Things that were difficult with only kinematics or only dynamics are actually a lot easier to solve with energy. And one of the reasons for that is actually the start here is that energy is considered a scalar unit. Now, what that means is it has no direction, it just has a magnitude. What that means for something like this is that generally for energy, you're always going to get a positive number. Now your change in energy can be negative, and we'll talk about like how we should interpret that. But for the most part, energy, you just get a positive number. Doesn't matter if you're going north or south or east or west, it's positive. If you do get a negative number, we'll talk about like what that means in the grand scheme of things. To think about energy and like this whole positive negative, I want us to start thinking of a system. So we have our system, and according to the first law of thermodynamics, the conservation of energy, energy can't be created or destroyed, can only be transferred. And so when we think of energy within a system, they're transferring within one another. But if energy ever transfers in or out of our system into our surroundings, we have a different name for that. We call that work. If you ever see work in a physics context, work is energy transfer. It's also in the same units as energy, which is joules. A lot of times you can get work using this formula. Work is equal to force times displacement times cosine of theta. Now this cosine of theta, where that's popping up, is basically something like this. You have a box. If I push this box to the right with a force and it goes like this displacement here, well, force times displacement is equal to work. But if my box is actually being pulled something like this, and this is my displacement, well, the force I need needs to be parallel with the displacement. So this is where I need to get the theta and then solve for it. You use some trig, solve for it. When you do all that, that's how you get the cosine theta. So work, you'll see in the formula sheet, the AP formula sheet, it's force parallel displacement. What they're basically saying is, yeah, we want the force and displacement that are in line with each other or parallel. So that's where you get that. If you notice here, well, force is a Newton, displacement's a meter, so a joule is equal to a Newton meter, and you can really break this up. I mean, F net's equal to MA. This is just going into units, so if you don't care about this, you don't need to pay attention too much. But newtons, kilogram, acceleration's meters per second squared. So a joule is hiding a lot. At this point, your joule has kilogram, meters. There's 2 meters here, so now it's meters squared over second squared. That is the same thing as a joule. I just want to show you all that these, this is not a base unit. It has units inside of it. If you just have joule, that's actually probably what most people will see for energy. What kind of energy is there? How do you know there's energy? Well, energy, I know an object has energy if it's moving. So if an object is moving, it has a specific name. We call that kinetic energy. The symbol for that on your AP equation sheet is K, and that will be equal to 1/2 mv squared. M being mass, v being velocity. I haven't really described what energy is. Energy is directly correlated to an object's mass. Generally, if you have more mass, you're going to have more energy. But like kinetic energy, we need to have velocity there. So if you're not moving, you don't have kinetic energy. The other kind of energy is generally not moving. It's a potential energy. So you could be moving, and that's how I like to think of it. We kind of split it up into 2 paths for AP physics, but there was a lot of mechanical energies or potential energies out there. We have gravity, and we have, I'll call it spring, sometimes you'll see anything with an elastic property would be the spring potential. U sub G, U is potential, sub G is the gravity, is equal to mg. They will put delta Y as your vertical change. Sometimes I'll just call it mgh, kind of just depends on what kind of information, what they call the variables. For a spring, U sub S is equal to 1/2 kx squared. Now, you may notice there's kind of a pattern going on here, and I'll kind of show you real quick, like, how do we come up with these equations, where do they come from? Just really quick. So I know work is equal to force times displacement. When I'm thinking about potential energy, I'm thinking about, you know, if my ball, I'm holding a ball, and I drop it from 1h versus 2h. Well, basically I know that if I bring the ball up higher, I'm going to be faster when I'm falling towards the ground, right? The more height you give it, the more kinetic energy you can get later. And that's because all the energy I put in to lift it up gets transformed into kinetic energy by the end. What you'll notice here is because we're scalar, because we kind of only care about the start and the finish, time doesn't really matter. We'll talk about that in a second. But the force here that's primarily involved is the force of gravity. So if my work of gravity is fighting the force of gravity, and my displacement I can just call h, well, if I plug everything in, Fg is equal to mg. Sorry about that. Mg. My height is there, and you'll notice that, oh, work G, mgh, that looks familiar. That looks like U sub G. So that's how we get these equations. We're just plugging into this force times displacement. The same thing happens with the spring. And I bring this up only because you're going to have a free response problem about Hooke's law. So what is Hooke's law? Hooke's law was the force of a spring formula. Now, you'll see it a couple ways. Sometimes you'll see it in absolute values, like K times X. Let me make that X bigger. It's not a subscript. It is the whole thing. K is your spring constant. The bigger your spring constant, the stronger your spring is. X is how much your spring deforms, so how much it stretches or compresses by. It could be either. This should be a positive number. That's what this means. Sometimes you'll see minus Kx, and that's what that means. Sorry, my laptop is getting mad at me. So force of spring is equal to K times X. If I use the same kind of formatting here, I can add in the displacement on my work formula would be another X. If you actually run the formula, you'll see that you can get like an area and you get this triangle that pops up, and the average displacement essentially is, that's where the 1/2 x squared comes from, and that's how we get that. If I were to map out the force of a spring to its displacement, I get this linear relationship. I get the K. K is equal to force of the spring over its displacement. This is a normal spring. If it doesn't do this, then you know it's not a normal spring. It doesn't act that elastically. To be elastic, it's an object that when you stretch it out goes back to its original shape. So the more elastic it is, the more likely it is to do that. Some objects are more elastic than others. We did an experiment where you have like a spring, and you know, it's hard to tell like what is my force of the spring, but what if you put like a 10 kilogram mass on it? Well, I know this object weighs 100 newtons. Its weight, it's Fg, or its weight is 100 newtons. So then I could say, well, instead of like mapping out Fs, I mapped out Fg versus X, and then I got this this slope here, and that's how I got my K. You should get a positive K if you actually do like absolute values, or if you don't do absolute values, then you could get a negative because Fg and X are always kind of in the opposite direction. But, the force of the spring. But yeah, that's so be familiar with Hooke's law and how to manipulate that, kind of like what we did for the lab. Moving on. Let's talk about conservation of energy. This is where most of this kind of class has culminated to. There's a couple ways to think of it. We could think of like a ball being dropped towards the ground. And so I'm going to make this LOL diagram. Why is it called LOL? Well, it looks like LOL. The O is the system, and that's where we're going to start. I'm going to put the ball, the earth, and the floor in my system. And so the ball is falling. It falls from a height h. Before, this will be position A, this will be position B. I'm going to figure out the energies at position A first. At position A, I'm up top, I'm not moving, so I'm all EG. Or I can call it UG if I want. So let's just say I'm all UG. The ball falls, it's so close to the ground, I'm basically going to say, yeah, there's a little gap there. I'm going to say it's basically at 0 height, but it's moving now. So now all my energy becomes K. And so now I can make this conservation of energy equation. Energy can't be created or destroyed, so UG must equal K. If it didn't equal K, I need to figure out why it doesn't equal K. The only other thing I could see taking up energy in this sort of scenario would be if it's not exactly at the ground, you have another UG. If there's air friction, I'd probably call that E dissipated. Now, where it gets kind of interesting is what if I took the Earth out of this problem here? So what if I do the exact same thing, but this time I don't include the Earth. It's just the ball and the floor. The Earth causes the force of gravity. If the force of gravity is not in my system, we don't call that energy transfer. If you remember back up top here, we don't call that energy, we call that work. So now, you know, I don't have a UG. I still have this EK at the end, or I'll call it K. And so what I'll call it, instead of UG, I'll call it work is equal to kinetic energy. And I can call it like work gravity if I want, but I have work here. It's just semantics. It's just definition based. AP Classroom will ask you questions about the system like that. If it's in your system, it's an energy. If it's out of your system, we call it work done on an object. Now, I give the scenario where it's the ball falling here, but I can give it as a different scenario, and it actually could mean the same thing. Like, if I did, so we have this scenario, but what if, instead of that, I do, it's the same thing, except it's an object, it's a ball, let's say, well, let me do it like a block. It's a block, same height off the ground as like the ball was, it's going down the ramp this time. The question is, what is different between these two? And if there's no friction, there's nothing like that going on, it's actually kind of the same problem here, at least the same setup. Let me do, so we have the cart, we have the floor, or the ramp, we have the earth. And so now, if I were to, you know, do this problem again, I get UG, I get K, and once again I get U sub G is equal to K, and I can plug in, you know, MGH is equal to 1/2 mv squared, and I could solve for these. If I want energy, I need to know the mass of the object, but if I just need to know velocity, you may notice that, oh, actually, like these m's cancel, 1/2 v squared is equal to gh, v is going to be equal to square root 2gh. I actually don't need the mass to solve for velocity, I just needed the height and knowing what gravitation is. What's interesting is this scenario here and this scenario also, very similar problems. The way we would have to solve them back in the past is you pretty much always need to figure out like time or acceleration or initial velocity. There's all these things you need to know to solve these problems over here. But with energy, you pretty much just need to know the speed of the object at certain points and like how far it's going to go. It does not matter on time. Without needing time, you really don't need a stopwatch for a lot of things, and you can figure things out. If you're smart about where to start with your energy conservation, like if I chose the block halfway down, this would be a very annoying problem to deal with, because instead of me saying like, oh, UG to all 1/2 mv squared, or you know, this part to this part, having to deal with this is annoying because it has some UG and it has some K. You know, I'll call it UG middle, K middle. You know, it has a little bit of both. They're not that, like, because I'm halfway down here, I do know it's half and half, but it'd be really hard to tell anywhere else on this ramp. So you gotta pick your spots carefully for where to do conservation of energy. That's the hard part, choosing the parts, where to actually take your energy equation. Once you do that correctly, you're good to go. The last thing I'm going to talk about here, sorry for a longer video, but I do need to mention power. So power is equal to work over time. And a lot of times these problems work out similarly. Work is, energy transfer. So if you just figure out what the energy transfer is divided by how long it takes, that tells you power. I like to think of power as efficiency in energy transfer. Yeah, you could do work in any amount of time and it counts as work, but if you take super long, I feel like it should pop up somewhere, and that's where it pops up is power. If you notice, this would be joules per second. So power, what it is watts. Watts are the SI unit for it. And that's pretty much it. There's a few other things in this unit, like there's gravitational work, which is, you'll see it's like UG is equal to M1, M2, big G over R, and there's a minus sign here. I wouldn't worry too much. If things have gravity, they have this universal gravitational energy. Don't worry about it for now. It will show up on your midterm, but it's not going to show up on this test. We'll explain it later. There's also instantaneous power. So you'll see this on your formula sheet. Power is equal to force times velocity. This is just another way to get power in a moment in time. You would use like the instantaneous velocity as well. Pretty much if you're using forces in an energy equation, you're probably just trying to figure out the work. Only in this case, you can like directly get the power at that moment. We never really did examples of these, so I wouldn't worry too much. We'll talk about it once again after this test, but if you ever see problems with this, you can kind of avoid it for now. But yeah, study those previous worksheets we've done. I think some good ones will be, we've got some, like these bar graphs are pretty good. And yeah, if y'all have any questions, let me know. I have a few extra questions here, which I call like AP style. I think like if you can do these equations or these questions, I think you're going to be pretty good. We might do a couple in class. I might do a couple videos on these, but up to y'all how much you want to study for this last major grade of the quarter before your midterm. So, all right, guys, I'll see you later.